It's safe to say that most, if not all, of our information about the greater universe comes purely from observational data. And this makes sense. The furthest thing we've ever sent away from us is Voyager 1, which is at 15.4 billion miles away from Earth and still going strong. 15 billion miles is a long way, but it's been cruising since 1977, and it's only about 0.25% closer to the nearest star than when it started. At this rate, and it's not getting any faster, it'll take 75,000 years just to get to Proxima Centauri. And it's not even pointed in the right direction. The closest thing we have to physical data about our universe is from the Parker Solar Probe, which we sent to the Sun in 2018. It's the closest spacecraft we've ever sent to the Sun, and the first thing to fly through the Sun's corona. At its closest distance to the Sun, the Parker Solar Probe will be 3.9 million miles away. Sound big? Well, remember that the Earth is 93 million miles away from the Sun, which is about 24 times further. Unfortunately, the nearest stars are so absurdly far away that we have no hope of getting to them in the relatively, or even not relatively, near future. So it's pretty clear that we can't just go out and poke stars to learn about them. Instead, we have to rely on what the stars are telling us, which typically comes in the form of radiation. Radiation, in the sense that I'm speaking, is anything that a star emits that's going close to the speed of light that we can receive here on Earth without moving an inch. One of the most important characteristics of this radiation is that it can move through space unhindered, so it can't be in the form of sound. While analyzing stars through sound would be pretty cool, even though it would be very loud, the vacuum of space puts an immediate end to anything. Anything that is except particles and waves that can travel through nothing. Well, they're not exactly traveling through nothing, they're traveling through space as their medium, but they don't require anything to propagate through, other than space itself. This leaves us with 3 detectable types of radiation: particles, gravitational waves, and electromagnetic radiation. We get radiated particles in the form of neutrinos, which are tiny, uncharged particles that go undetected most of the time. They can fly through space at a significant portion of the speed of light, which is helped by the fact that their mass is almost zero. Without getting too deep into particle physics, what makes neutrinos special is that they don't have any charge and they basically don't have any mass, which makes it very difficult to interact with them. In fact, neutrinos are passing through us right now, but you wouldn't know anything about it because there's no interactions. There are 3 flavors of neutrinos, and one of those, the electron neutrino, interacts with normal matter. This makes it possible to detect them, although very, very difficult. The Super Kamiokande detector in Japan is a great example of a neutrino detector. The Kamiokande detector is a giant tank of ultra-pure water. Neutrinos interact with electrons in that water to create a particle that is faster than the speed of light in water, but slower than the speed of light in a vacuum. This creates the optical equivalent of a sonic boom, which we can detect. Unfortunately, the other 2 flavors of neutrinos don't interact with electrons, so we can only see their byproducts, not detect them directly. Neutrinos are the result of stars just existing. They come from our sun all the time, but they can also be a product of a supernova. While neutrino detection is relatively new, that means there's a lot to learn about it. Neutrino radiation has helped develop the standard model of the universe, as well as more information about a bunch of other high-ion energy processes, like black holes and supernovas. Speaking of black holes, they can create one of the other types of radiation that we see, which is gravitational waves. General relativity dictates that objects with large gravitational fields distort time and space around them. At a very basic level, this is because light is affected by gravity, and since light always has to travel at the speed of light, no matter the frame of reference, space and time have to be the variables. While the distortion in space-time isn't noticeable in our day-to-day lives, it can propagate outward from a source at the speed of light, which means that fluctuation in the distortion of space-time can be detected, and this is detectable at the same time that the light reaches us. So 2 stars orbiting each other and eventually merging together can cause gravitational waves, and can also cause us to be able to see that merger. We can detect gravitational waves by the interference pattern between 2 perpendicular lasers. We don't have a lot of time, so I'm not going to get too deep into that, but if you want to learn more about gravitational waves and their detection, look up LIGO, and I'll leave some links in the description. But above all else, our favorite way to look into the cosmos has been through electromagnetic radiation. As humans, we've been looking up into the sky as long as we've been around, and now we have better and better equipment to look up into the sky with more precision than ever before. But before we can see anything, some light has to be emitted, which starts with a star. Stars get their energy by fusing lighter elements into heavier ones. A little bit of mass disappears and that mass turns into energy. That mass gets emitted as light in accordance with Einstein's mass-energy equivalence formula, better known as E equals mc squared. Now, the peculiar thing about light coming from stars is we can tell a lot about the star just by the frequency of the light. The emission spectrum of a star follows very closely the laws of blackbody radiation, which dictates certain behaviors that something emitting light will have. Wien's law dictates that the peak wavelength of the emitted light, that is, the wavelength that makes up the most of the emitted wavelengths, is inversely proportional to the temperature of the source. As a general equation, this simplifies to the wavelength being proportional to 1 over the temperature of a star in Kelvin. Given this equation, we can determine the temperature of a star just based on its color. Now, the conventional standard is that red is hot and blue is cold, but blackbody radiation flips this on its head. Stars that radiate in the red part of the spectrum are significantly cooler than their blue counterparts. Red giants are huge, but based on their color, we know that they're counterintuitively cooler than the smaller, bluer stars. However, just because one star is hotter than another doesn't make it radiate more energy. Another equation for blackbodies is the Stefan-Boltzmann law. It dictates that the power radiated by a star is directly proportional to its surface area times its temperature to the power of 4. To get equivalency from proportionality, we multiply the right side by this constant sigma, which turns this proportional sign into an equal sign. Plus, it makes the units work for all you physicists out there. So the size of a star does matter in how much power it radiates. Based on how much light we receive from a star, as well as what frequencies we're receiving, we can determine a lot about what's going on inside the star, such as what materials it's made of, what materials it's fusing. We'll talk about that a bit later. To be quite honest though, it's impressive that we can see stars at all, which really goes to show how bright and massive they really are. As the distance from a light source increases, the amount of light you receive from that light source goes down a whole lot in accordance with the inverse square law. Let's imagine a point light source shining through an imaginary 1 meter squared area that's a meter away from it. For the purposes of this example, let's say there's 100 watts of power going through that square. That means 100 joules of energy in the form of light every second going through this 1 meter squared area at 1 meter away from the light source. If we double the distance from the light source to the square, we actually have a lot less light going through the square, because the power is spread out over the same angular distance, but because you're further away, there's less of it. So projected into 3 dimensions, we actually have to have 4 times the area to get that 100 watts of power. So for a star, the intensity is equal to 1 over 4 pi r squared, following the area of a sphere. So while a star may radiate a tremendous amount of energy, we only get a tiny fraction of that because light disperses very quickly. If a star is twice as far away, we only get a quarter of the light. This makes it so that we need better and better telescopes to look further and further away so that we can learn more and more about our universe. Because stars are so incredibly far away that we only get a tiny fraction of their total energy. One of the other things that gets in the way of observational astronomy, it does just that. It gets in the way. Different frequencies of light are blocked by different materials. Take our atmosphere as an example. We have evolved to see in the visible spectrum because our sun emits in the visible spectrum and our atmosphere lets the visible spectrum through. But there are lots of other frequencies of light that don't get let through by the atmosphere. For example, lots of our ultraviolet light gets blocked, and most of the infrared does as well. The only other band of frequencies that gets let through by the atmosphere is radio waves. So there's all sorts of stuff in space that can get in the way, but by using different frequencies of light, we can see through it. Check out this image of the pillars of creation taken by the Hubble Space Telescope. Now compare it with this one taken by the James Webb Space Telescope. They're in different ranges of frequencies, and so we can see different things. We get to see through some clouds, and we get to see what's behind them. There are tons of other cool things to see if we just start looking in frequencies that we can't see with our eyes. But because of the way the atmosphere works, ground-based telescopes have to be either in the visible spectrum or in the radio spectrum. None of the other light gets through, which means that not all of our astronomy can be done from Earth's surface. We have to send stuff to space. This is because one of the most crucial bands of frequencies is the infrared, because most stars and galaxies that are far away are moving away from us. While this doesn't seem like it would matter immediately, the relative velocity between a light source and its observer matters a ton to the frequency that's observed. Light sources that are moving away from us, so stars, are redshifted due to the Doppler effect. A wave with a moving source basically has its peaks and valleys stretched or shrunk based on where you're looking. Light propagates outwards like this, but if you start moving the source, parts of that wavelength are compressed and parts are expanded. So the apparent frequency of light will change based on where you're observing from. If the source is moving towards you, it gets blue shifted. If the source is moving away from you, it gets red shifted. One of the most interesting things we've observed about the universe is that the further things are away from us, the more redshifted they tend to be. This means in order to be looking at the most distant stars, we need to be looking in redder frequencies of light, so the infrared. One of the side effects of this knowledge, that further things tend to be more redshifted, is that we've deduced that the universe seems to be expanding. When we look at the most distant galaxies, we can see that they're significantly more redshifted than the closer ones. That rules out the possibility that we, as the observer, are just moving away from everything else. Plus, it's the same in all directions. The only logical explanation is that the universe is expanding. Imagine it like this. Two galaxies emitting the same frequency of light are 1 and 2 arbitrary units from us, the observer. When the universe expands, like it's being stretched, the closer galaxy gets twice as far away, and the further galaxy gets twice as far away. Everything gets twice as far away from us. However, the further galaxy moved twice the distance, because in order to move twice as far away and starting twice as far away from us, it actually moved twice the distance in the same amount of time as the closer galaxy. Since velocity is distance over time, and the time is the same, the further galaxy has twice the velocity of the closer one. And like I just mentioned, this causes it to be more redshifted. So to look further away from us, we need to look into the infrared to be able to see everything. But we want to do blackbody analysis on this, right? We want to be able to take that peak frequency and figure out what the star is made of. So if that frequency has been redshifted and the peak frequency isn't what it used to be, how are we going to do that? Well, based on the properties of matter, we can determine what the frequencies should be. Every element absorbs and emits different frequencies of light when its electrons are interacted with. Given appropriate equipment, this is plainly visible in the emission spectra of stars. Each element leaves a specific barcode of spectral lines that we can detect and then figure out exactly how redshifted or blue shifted that star is. For example, hydrogen leaves 4 specific spectral lines in everything that it emits. These 4 wavelengths will always be a particular distance apart, no matter how redshifted the star is. So we can always pick out hydrogen from an emission spectrum and determine, hey, that star is made of hydrogen. But we can also figure out what the true frequencies of emission are, which means we can figure out that peak frequency and figure out the temperature of the star and how it's fusing. Every single element will do something similar, and while they're not all as simple as hydrogen, we can use the barcodes created by elements in their stars to figure out what stars are made of and how fast they're going away from us. So once we know the true frequency, we can use this equation to figure out exactly how the star is supposed to look. The wavelength that we see minus the wavelength that is actually emitted over the wavelength that is actually emitted is approximately equal, and to a very good degree, the velocity of the star moving away from us over the speed of light. We know what frequency we see, we know what frequency it actually is, and we know the speed of light since it's a constant, so we can solve for the velocity v. Lots and lots of observational data has also shown that there is a relationship between how far something is away and how redshifted it is. We can estimate the distance to something in space through a variety of methods. Some of them are easier than others, some of them work better closer, some work better further. Radar ranging works within about an hour. We basically shine a giant radio flashlight in the sky and see what bounces back and when it bounces back. It only works within about a light hour from us, so it's not very useful for stars, in fact at all. Anything further than that, we're going to use stellar parallax. Parallax uses the apparent displacement of a star based on the background stars to determine its location. Do me a favor and hold out your finger or your thumb at arm's length. And close one eye. Now look where it is on the wall. My thumb is currently directly covering the camera lens. But if you switch eyes, your thumb is going to move. That's the same concept as stellar parallax. Between June and December, 6 months apart, we can take 2 pictures of a star, figure out how it has moved in relation to the background stars, do some trigonometry, and figure out how far away the star is. This method is so convenient we actually made a new unit for it, the parsec. Contrary to Han Solo's line in Star Wars, the parsec is actually a unit of distance. If the smallest angle made by the Earth, the Sun, and the star is 1 arcsecond, the distance between the Sun and the star is 1 parsec, which is approximately equal to 3¼ light years. The problem is eventually the angle becomes so small that we can no longer accurately measure it. Around 200 parsecs away, this method starts to become unreliable. For anything further than 200 parsecs, we can use what's called spectroscopic parallax. We start by measuring the brightness and spectral type of a star, even though we don't know how far away it is. Assuming it's on the main sequence, we can make an estimate for the luminosity of the star. The main sequence is stars that are fusing hydrogen, and this is about 90% of stars in the sky. So this assumption is a fair one. Based on the luminosity we calculate and the brightness we receive, we can apply the inverse square square law to get how far away that star is. Unfortunately, all good things must come to an end, and so this method starts to fall apart around 10,000 parsecs. After this point, we have to rely on a certain type of star that has a standard luminosity. Cepheid variable stars are stars that get brighter and dimmer with a consistent period. That period is directly related to their absolute luminosity. Variable stars that pulse quickly have a lower luminosity, and those that are slower have a higher luminosity. We can use that knowledge to figure out how far away a Cepheid variable star is, and then the stars that are around it. That known luminosity can be used to measure to about 25 million parsecs, which is hugely helpful to astronomers hoping to estimate distance. But further than 25 million parsecs, we have the Thule-Fisher relation, which can be used up to 200 million parsecs away. There's a well-defined relationship between how quickly a galaxy is rotating and its luminosity. As a galaxy spins, we can measure one side of it as being red-shifted and one side as being blue-shifted. So measuring the galaxy as a whole, this takes the frequency range from a smaller band and broadens it just a little bit. Once we know how much the band broadens, we can figure out how quickly that galaxy is rotating. If we know the rotation rate, then we know how luminous it is, and now that we know how luminous it is, we can make an estimate of how far away it is. The last step of this chain is standard candles, which are objects of known luminous intensity that we can use again to measure distance. For example, type 1a supernovae are a type of standard candle. Because they're a binary system of stars with one star, kind of like a vampire sucking the life out of another one and getting more massive, we know exactly how much mass it's going to have when it goes supernova. Because we know how much mass it has, we know exactly how luminous it's going to be. And again, now that we know the luminosity, we know how far away it is. There are lots of other types of standard candles in the universe. This is just one of them, but they're all super helpful in determining distance. In essence, astronomers use a bunch of tools just manipulating and measuring light to figure out how far away everything is in the universe. But to get all this light, what little we can, we need some pretty big telescopes here on Earth. How big? Well, I can tell you exactly, but it depends on what we're trying to see. Light passing through an opening, called an aperture, will interfere with itself depending on the size of that aperture. The bigger the aperture, or in the case of a telescope, the bigger the mirror, the less the light will interfere with itself. So based on the angular separation of two light sources and the wavelength that you're trying to detect, you can figure out how big your mirror needs to be. That is, if you want to be able to distinguish those 2-point light sources. All this information gets condensed into this equation, where the angular resolution in arcseconds is equal to 0.25 times the wavelength in micrometers over the mirror diameter of the telescope in meters. We can switch the terms through algebra of the angular separation and the size of the mirror to figure out exactly how big our mirror needs to be based on what we're trying to see. The longer the wavelength, the bigger the mirror needs to be. The smaller the wavelength, the smaller it can be. This is why we have radio telescopes such as this one with such giant mirrors, whereas X-ray telescopes can be significantly smaller. But the bigger the mirror, the better the angular resolution. So we can pretty much make the argument that in the case of telescopes, bigger is almost always better. So with some of the most sensitive equipment in the world and a bunch of math, we can figure out exactly what's going on in stars that would take us millions of years to get to. And that's one of the things I think is so cool about astrophysics. There's so much that we've learned about the universe, and the only thing that we have is what the stars tell us. And that's pretty special. Thanks for watching.